Presentation visible? Hello, Jahangir, can you hear me?
Yes, sir.
I guess I'm sharing this presentation with you. Is it visible?
Yes, sir. Visible.
Okay. Good morning to all of you. My name is Kalimullah. I'm a research scholar in the Department of Information Technology in NIT Srinagar. Today we will discuss what this IoT and big data is. We will start with directly with the data. What actually the data is, how it's created, what are the techniques to process this data. This is all which we are going to learn today. I am sharing this screen with you. There are 2 million queries. Google receives 2 million queries every minute. The Facebook data, websites being created every minute, 571 websites are created. YouTube users upload 48 hours of videos, 48 hours in 1 minute. So we can say that there is a huge amount of data that's being generated globally from different geographical locations. And this data that's being generated, 90% of the world's data has been created in past 2 years. There are billions of devices, small devices that generate data, and that data is being uploaded onto the clouds, stored in hard drives and different geographical locations. This data generation, we can see, I will show you a website. I guess this will be visible to you. I will open Internet Live Stats is a website. Is it visible?
Yes, yes.
Okay. So I'm opening this website. Here we can see internet users in the world at this present time. These are the internet live stats. Total number of websites here. Emails sent today up to 10 a.m. this morning. This many, this number of emails have been sent today. Then the Google search, blogs written, and the Twitter posts today. This is the number of YouTube videos being viewed today, photos uploaded on Instagram, and different social active users on Facebook, Google Plus, Twitter. And this is the all data that is being created across the globe. And I have inserted this slide yesterday. That will be the timing 6:43 yesterday evening. This was the number of users globally. So we can see when the number of users on the internet, this huge number of users when we have, then we must see how much data we are producing globally. And this data, who is generating this data? I will say everyone is generating data. Anything is generating data. Anybody is generating data. Whatever thing we have in the world, I guess everyone is generating, from healthcare to homes to retail.
I think we have lost connection with the expert because there is a power shutdown. So just wait for a second. Hope he will join us soon. Am I audible, Mr. Kalimullah sir? think, Kaleem, your voice is not audible.
Am I audible now?
Now you are audible.
Okay, okay. There was some technical problem on my side. So we were discussing who is generating this data. Everyone from healthcare to homes to retail, energy, manufacturing, mobility, transportation, logistics, media. Everyone is uh, consuming data and producing data. So next step, we will what we have to do this what we have to do with this data. The basic processing of this data is we want to analyze this data because we have data, we collect it, we store that data in some databases or some hard drives or some cloud servers, storage servers, and then we see the behavior, we see the data analysis, we see the behavior of a person, behavior of a group, behavior of community as a whole. So we are processing this IoT data. What actually this IoT data in the last presentation yesterday, I guess IoT and big data, all the data sources, how data is generated, how data is seen, and how it's processed. It was discussed in yesterday's lecture. I was keenly observing that Dr. Ehsan Chasti's lecture. So here we will simply move from IoT data. You know it, how devices are doing, how creating data. The next point is that the basic objective of this IoT devices, Internet of Things devices, to sense. They are sensing. Wherever we deploy those devices, those nodes, those modes, whatever capacity which we are using, we have devices and we are simply uh, making them to sense their environment. And when the data grows continuously, there are, I guess, yesterday's news it is that we have in Delhi city alone, it has surpassed most developed countries in terms of number of cameras being installed in streets, in markets, in workplaces, in community centers, and other locations. It means you just imagine how much data is being processed, how much data is being generated by these cameras, these video cameras. What is the purpose of generating this data? The basic objective is the security. People, we want to make sure that our people are secure. But there are some other things which we can do with this data. Simply, we can see the behavior of people using sentiment analysis, using other kind of algorithms and techniques to process this data and see the trends within that data. We have a lot of data, but the main thing is we must uh, work on that data. We must process on that data, analyze it, and get the results. See the hidden features within that. Now, when the data grows beyond the capacity, simply what how I define big data. IoT data and big data. Both are data. The basic entity is data. We work on data because data is the new soil. It is the oxygen for next generation. We must see our applications, apps in mobile phones which have data, weather data being stored from past 150, 5 to 10 decades, and we are predicting out of that. So this data is changing and it shows no sign of stopping. It's growing day by day. It's growing day by day. We have social media. It's generating data at an enormous pace. We must somehow sometimes stop and think why this data is being stored, what those servers are doing with this data. Along with that change, the scope and scale of data are continuously increasing. In big data, what we have, we call it, we have some V's. Volume. When the volume of the data grows so high, when the velocity of the data, speed of the data is so high, from 1G to 2G, second generation, to third generation, to fourth generation, and we are moving towards the fifth generation. The velocity factor will be the main thing in big data. And velocity, uh, when we compare the velocities of third generation and fourth generation, the fourth generation is much better than third generation. But when we move beyond, what is the future, the fifth generation, the fifth generation will have much more velocity. So we will have more and more big data with the next fifth generation. So this data is changing and it has no signs, it shows no signs of stopping. When it has no signs of stopping, and this data will grow continuously. When this data will grow continuously, we must have resources to store it. We must have resources to process it, resources to analyze it. So the second V, volume, the velocity, and the variety of data. We have data in the form of, with extensions, MP3, MP4, PDF, log files, CSV files, and data of different categories we have. So big data consists of mainly three things. There are some other V's that define big data. Like the first thing is volume, velocity, and variety. We have a huge volume of data. The velocity is a bit less at this time, but it's manageable. But if the velocity will go on increasing, can you imagine, in 2006 I was using a plan, 1 GB plan per month for my mobile phone at a speed of 2G. By the end of the month, I could hardly uh, use 1 GB, 1 gigabyte of data for the whole month. When it came to 3G, from second generation to third generation, it was like we were able to use 1 GB, 2 GBs, 15 GBs, 20 GBs. But when it came to 4 GB, I'm daily using 1 to 2 GBs of data. Just comparing, going back 15 years or 12 or 13 years, we were using 1 gigabyte of data for the whole month. Today, when the velocity of the data has increased, we are able to use 2 GB gigabytes of data per day, 3, 4, 5, depending upon our needs. So when we will move to the fifth generation, 5G, the amount of data, the velocity of data will increase. This velocity will increase the number of volume of data. And by default, when velocity increases, the volume goes up. And the volume goes up, it means data from multiple sources is being added to our databases, to our data servers. It means the variety factor is also going. There are some other V's like value. There is a veracity, means, and other V's, but the main three V's which define big data is volume, velocity, and variety. But we have to see the impact of this data, impact of 5G, fifth generation, with this data. So when we compare it, when we uh, uh, see the comparison between two, when the velocity, the generation will go up, one generation we'll move to the next generation, that's fifth generation, there will be an enormous increase in the velocity of data. When the velocity increases, by default, the volume increases. When the volume and velocity both increase, there is a direct relationship between, there must be variety of data that will go on increasing. When we move 15 years back, the video format of the data, MP4, MPEG, or some other formats in which we store videos, it was much less on internet. But when the volume increased from second generation to third, third to fourth, volume increase. We have a lot of videos. If you must be having an eye on Facebook from 2006 to 2010 or 13, there were very much less amount of videos, only photos and some text was circulating around Facebook. But when third generation came, we saw live features, live videos, and videos of uh, higher quality, and hours of videos being circulated around. So big data is about data, simple and plain. Yes, you can add all sort of adjectives when talking about big data, but at the end of the day it's all data. And we see this IoT is about data, devices, and connectivity. IoT, Internet of Things, a device, a small device generating data, a device generating data with a connectivity. It must be connected to some other device with high capacity and with high processing, so that this data generated must be offloaded to the next station. Data, big and small, in front and center in the world, IoT world of connected devices. So, what big data is a huge volume, velocity, and variety of information assets that require new forms of processing to enable enhanced decision making, inside discovery and process optimization. This is the Gartner's definition of big data. It was Gartner who coined it in 2012. But I am a student of big data from 2014 onwards. I'm working on this subject. What I believe, what I saw, big data is, it's like an any data that exceeds current capability of processing can be regarded as big data. For example, when I teach my students about big data, I simply move on like this. We I tell them, in your opinion, who you call a rich person? A person who can afford one time meals, not two times. According to his definition, and a rich person is one who has meals twice a day. A person who has meals twice and some basic needs, he can fulfill basic needs. In his definition, the definition of rich is different. But as per us, the richest person of the world, you tell him who is the rich, who is rich, his definition of rich will be different. In the similar way, for my PC computer, big data is a data that my system cannot handle. For a server, big data is a data that the server cannot handle. My system has a RAM of 16 GB, a good hard disk, and a good processor. But there are some occasions where my system failed go for processing. It stops when I have a huge amount of data to process, when I deal with big data. So simply, in simple terms, we take a machine, ideal machine with a good processing, good RAM, and good storage, and then process some data on it. If the data is being processed, we simply call it processing. But when the RAM and the processing and the storage, it will not work with the amount of data, we call it big data. Simply defining this big data at different levels is different. So if we'll take an ideal machine, a powerful machine, when it works with data, if there is some amount of data where it will fail, if I have a 1 terabyte of RAM, for example, there must be some data which is beyond this capacity. If I will put that data into that system, it means that system will stop functioning. It will not work. I call it big data. For me, big data is a data that my machine cannot handle. So simply, the data we have, it's both structured and unstructured. What is this structured data? Structured data, a data that's in order, that's placed in rows and columns and everything. like my Excel data, CSV data. We have some XML data, JSON data that's unstructured. The data does not have any structure. We have data being stored on websites and other locations. We call it unstructured data. So this whole ecosystem of big data is like, this is the, on the extreme right side, we have a big data service customer. It requests for the services to a big data service provider. This service provider will check the services it has, the data, which it will check this request from the user. For example, there are some data occasions when I request for data. If the data is already in structured format, it will get the data from me. It will first deliver me, I will request the data, it will give me the metadata. Metadata means it's a data about data. For example, I have a data placed at a location. I know the address of that location. I give you the this data provider will, data broker and supplier will give us that metadata, information about data. Simply, I can go to that location and I can access the data. There is one more thing here. That's data crawling. I will show you. I was just working on this Python. Okay, just I will show you a demonstration here. I was this one scrap. We call it here in the presentation. We have data crawling or data request or data crawling, or we call it data scrapping. I was doing, there is a library, what, or I can say that is a inbuilt package in Python. We call it beautiful soup. I use the beautiful soup. For example, this is the data. I'm using this. I'm NIT Sri.ac.in is the website. Simply, I will click it. Okay, NIT Sri. Okay, this is the website, and I will move to the departments. This is information technology department, and it has some information on it. This data is an XML data or JSON data. This is not structured. The data is randomly distributed. Here is information. This is the information about department. On the extreme left side, we have department, about, gallery, HOD, and some other things. News on the right side, timetable, students. And this data, I want to download the data, crawl it, store it somewhere. We simply, what we do, what I did, I installed I will run this code. I'm installing this beautiful soup. I installed it, and then, okay, in the third, I will import the packages from this beautiful soup, and here I will get requests.get nit3.in/departments/ because this is our own website. This data crawling or data scrapping, this is illegal if you will do some illegal kind of a thing, but this is an organization in which I'm working. That's why I have put this. How can you download data that's not in the formatted way? The data that is being scattered around is not in any format. So first I will get the data. So here I need this URLs data, and in the first attempt, what I need, html.parser I am adding, and soup.prettify. So I will not, if I will not use this prettify here, the data will, first I will run it. Okay, here this data from the website, from this page, right, like here, if I will move to view source page, and this is the data in this HTML data of my website. This IT department's web page. But when I will move here, this is the whole data which I have. I have used this Prettify here. If I will remove this Prettify for a minute, Control X, I will run it. The data is being crawled, but it is in a jumbled way. We have not indentations, but that Prettify, soup.prettify will download this data or crawl this data in a good format like we have in HTML, where we can identify indentations, which opening is related to which closing. So I have downloaded this, but I do not need this data. What I am supposed to, I have to see, I have to get this, sorry, I need this data, this, the text that is being stored here. I don't need any programming kind of a data and HTML data, which will be useless for the users who are working, who need data, end users. So simply I will get soup. I will remove this Prettify here. Just a minute. I will use this Prettify here. Soup. I will remove that Prettify. I will check here soup dot underscore get underscore text. I will get the text out of that. When I will run it, the text that is being written on my page is NIT, National Institute of Technology, Srinagar, and moving down, that's toggle navigation, home, information technology, login, this all, and this is the information that all the things that are placed on that web page. It's here. So the information that's being placed here is simply copied and then put it in a formatted way. Then if I will check what is the title, I will check here soup.title, print this title in a prettified way. The title of this page is sorry, NIT Srinagar, National Institute of Technology Srinagar. When I will move to that page, the title is National Institute of Technology Srinagar. So there are some other, you can move to that thing. You can go to the advanced things like that. When we move to when we say we are crawling data, when we want to scrap data from different websites, and I want to, just like if I'm doing research or any kind of a thing in media, I want to copy all the newspapers, data from different newspapers, data that's being published. I can get that easily without going to the website and copying the content and pasting it somewhere. I will use data scraping here, data crawling here, and then simply will put that data, uh, write a simple code, and on the basis of that code, I will crawl that data, and I will place it somewhere in any location, in some location, and we don't need to go and copy and paste data always. We can have some instances in which we can run daily this code on daily basis, and that data will be extracted on daily basis. There are some other tools, like in which we can there are some paid tools through which we can crawl data. The data crawling is valid and it is useful and it is authentic, or I can say good, if it's used in a for progressive purposes. If I'm downloading some content and then without mentioning their name, without mentioning their without citing them, I will using them. I must cite the data and use it. Then it's not illegal. It becomes legal when we crawl data and without mentioning the sources of data, and simply going for some publications and other kind of things which we know the ethics of research and other kind of things. So data crawling, if we are crawling data and using it for useful purposes, then it is good. So the next slide, which we will move, this is what is the processing. The first point is big data. In big data, we have data collection. This collection kind of a thing is done with the help of IoT devices, IoT nodes, and then data pre-processing. There are some occasions where we can see most of the cases in Internet of Things, IoT devices are so small that they cannot process the data. They simply capture it, sense it, and then pass to the next uh, node, pass to the next connected node. And up to that point, if there is a device which has some processing capabilities, we can go for some initial pre-processing. But if some IoT device is such that it produces data and it has some capability to process data, we will go for some pre-processing. The next stage of this is we will see the data storage. We will store data. When we will store this data at some server, at some inbuilt internal memory, or some other location. There are different locations where we can save. There is a chance that we can save it on a local device, on some cloud location, or some other. And the next point is data analysis. Analyzing this data. Actually, the main objective of storing this data, processing this data, and collecting this data, there is the main, we must analyze it. If we will not analyze, there are some uh, trillions of bytes of data, picobytes of data, zettabytes of data that's being stored. But if we do not know how to use it, where to use it, how to analyze it, how to find hidden patterns, there is no fun of collecting that data. We must not collect only data for some dummy purposes, just to make things are happening and where this is a routine checkup. No, we must go for some analysis. We are answering the questionnaires, question banks. When we answer them, that analysis must be done on that data. Then when we analyze the data, we get some graphs, graphical representation of data. Because if I have a page full of text and similar information is being replicated in the form of a visualization, a graph, a histogram, a bar plot, a chart, or some other kind of a thing, the visualization is important. We must have some methods to visualize data graphically. The graphical representation is much more attractive to the audience in comparison to the text that's being shown on the screen. The managerial level decision making is totally dependent on the visualization. If the data is properly visualized in a pie chart, we have three entities, 1, 2, and 3. We have to see the impact of both all the three entities on a particular thing. We simply plot a histogram, see how much uh, impact they have. Simply plot a pie chart. We have a square in which we will sorry, a circle. We will cut it into three pieces, and we will have some pies, three pies that will show how much, what is the actual analysis of the data. And then we have data management. We have to manage that data. We have to, the management has a lot of things to do. And then we have data security and protection. We have to secure the data and protect the data. These are the whole process, the seven processing, data processing, and like I said, this is the data, big data processing, how we process this big data. Now, this IoT and data, there are some challenges. 44% of people believe that there was too much data to analyze effectively. We have a lot of data when we can effectively analyze it. 36% said that it was difficult to capture the data in the first place. It's difficult to capture data. 20% person say the data was not captured reliably. The reliability of data was not there. 19% say the data was captured that too slowly to be useful. Like in live streams, if I am running a live stream on some channel and I'm showing some cricket match or a football match or some other live match uh, with a delay of 2 to 3 minutes, there is no fun. There's data being captured too slowly to be useful. Now it's not useful. There's a pain in it when we see we're waiting, eagerly waiting for the next ball. If there is a sync between the cricket updates and the cricket streams, then it makes some sense. But if there is no sync between these two, it does not make any sense. Once the data is captured, 27% say that we're not sure that to do to what to do it for, and why unsure what questions to ask. We capture data, but we do not know how to use it, why to use it, how to raise questions for that data, for which purpose we are generating this data. 26% say that data analysis process was too slow to be actionable. There was some spontaneous decision in an aircraft that does not allow even a nanosecond delay. If we will make a decision after a minute, within that minute the plane must have been crashed. We must act. We must uh, we must not be too slow to be actionable. 24% said that business processes were too rigid to allow them to act on their findings. Because there are some occasions where some organizations find something, but they will not allow data analysts, data scientists to work on that data. While cost is often a limiting factor in many technology decisions for IoT stakeholders, ease of use appears to be more pressing than the issue than the cost. We simply can understand this in before the batch processings, before 90s, after the Microsoft graphical user interface, the ease of use using this personal computer, it revolutionized the world. So moving now, up to this point we have discussed two things broadly. One was that we discussed IoT. Second, we discussed big data. The IoT and big data, they have what they have. IoT generates data. It does not have a huge processing or some processing. The data is being offloaded, sent to some other location, sent to some other connected device where it is being stored. That stored data can be sent to some other location where it is being processed, where it's being analyzed. And when the data grows from one generation to second, second to third, third to fourth, and from fourth it will go to five. When the velocity of the data moves on increasing, it will increase the volume of the data. When the volume of the data is increased, it will automatically we will have more variety of data. When the variety of data is there, our personal computers will not be able to process the data. When our personal machines will not be able to process, what is the solution? So in that case, we call this whole kind of data as a big data. When our machines, personal machines, are not able to store the data, we move to the cloud to access the data, to store the data, and then we will be accessing the data from cloud. So up to this time stage, we have a structure and architecture. In that architecture, at the bottom, we have IoT devices. At the top, we have cloud. But from moving directly from IoT to cloud every time, it's a challenging kind of thing. We will have some problems. What we will do now? We are inserting a fog device. Like we have at bottom zero, ground zero, we are here. At the top, we have cloud. But when we have some rainy season, we have fog that's between cloud and that ground. That fog covers the area. Uh, we cannot see clouds, but we can directly see fog. In the similar way, at the ground zero, we have IoT devices. At the top, we have cloud servers, data servers, and storage servers, and processing servers, some other servers. And in between cloud and fog, in between cloud and IoT, we have fog devices. Those fog devices have some capability and capacity to handle data, to process it, to analyze it, to do some useful work. If we have some data, we have to access some data. My IoT devices are connected to a fog node. Instead of going every time to the cloud, fog is placed between much closer to the IoT devices. It is a simple thing. If I'm here from Srinagar, I'm in governance. What we have in governance, in states, we have a government. When we move to the center, we have a central government and we have state government. In order to, if we have to address government on some issue, we have to solve an issue at the ground level. What we will do, we will not move to the center from here Srinagar to Delhi. We will approach the state government. If it is within the limits of state government, the issue will be sorted here. But if the state government is unable to perform it, unable to execute it, and there are some problems to execute here, they will move to the center, get some more things, get some more resources from the center. That's the cloud. You just consider central government as a cloud, state government as a fog, and a user as an IoT device. Whenever an IoT device wants to connect to the fog node, it will get connected. But the issues, but the processing, if the processing is within the limits of state government, they will do it. But if it's not within the limits, they will move to the center. But who will move to the center? That's the fog node, state government. That person, it's hard, that it's difficult that everyone should move to the cloud and ask them for some help, some resources. We must make sure that there is an intermediate layer in which we have placed a fog node or edge device. That edge device will do our processing. But in case in sometimes where our edge device has a limited processing, limited storage, or some other kind of thing, so in that case, we will move to the cloud server. So we have to address this issue. We have Hadoop as a solution to this big data. Hadoop is it works on a master slave architecture. There are two important things which we must know about Hadoop. The first thing is that Hadoop works on a map reduce kind of a thing. And the second, we can simply say it has two layers. One layer is map reduce layer and other is HDFS layer. In map reduce layer, we have master nodes and slave nodes. In HDFS, it works both in master node as well as slave nodes. At the master map reduce, we have a task tracker and a job tracker. Task tracker and job tracker get the things done. So first we must understand what we are going through. We are now working on big data, the data that is being generated by IoT devices and stored at some fog or cloud, and then that processing of the big data is not done in a traditional way because the data is huge. So we have a task tracker and a job tracker. So it will get the work done from slaves. There are n number of slaves. It will we will simply say the master node can simply divide the task among different task trackers. Those task trackers will execute the data, execute that task, and then uh, in a like divide and conquer, we will divide the task among slaves, and then at the conquering phase we will conquer it. Job tracker will do this all at first. In the first stage we have map stage, and the second stage is reducing stage. The map is divide, reduce is the conquer. In map, what we will see, uh, we will map our, searching some Google, searching something on Google. I want to Google something. I put it on Google search bar and then write. It will first map it to number of slaves, and then it will reduce the data. It will find millions of results, but the most appropriate results will be uh, seen by the user at the screen because it's due to the reducing phase. And it uses a database, sorry, a file structure. We call it HDFS file structure, Hadoop distributed file system. That file system has some name nodes and data nodes. Name node makes, it's like the mitochondria. Like we have mitochondria in cell. Similarly, we have name node and job tracker working similarly. They make other people to work. They allow them to work, allow them to work. So data nodes perform the actual storage or some kind of whatever kind of a thing. So name node makes them execute. It acts like a manager and makes things uh, easier for us. So this is the name node and this is the data node. And in HDFS architecture, we call it DFS, distributed file system. And this HDFS architecture is being used by Google. Hadoop distributed file system architecture is being used by Google for their files distributed file system. We have name nodes, we have data nodes. In data nodes, where the actual data is being stored in the form of blocks, we have data nodes on the right side and data nodes on the left side. They are located in some racks, rack 1 and rack 2. There are some operations. If I have a metadata operation, I want to search something in it, means I have a metadata. My query is to find a particular data item. For example, search NIT Srinagar from internet. It is the metadata. It's an information about a particular data. Name node, what it does, it has a data. It tries to find, and the minimum block in this search, it's Google, it's HDFS use 64 MB block, and data nodes placed in different racks, and within racks it has blocks of data being organized in a proper way. And whenever we store any data item in anywhere, it has an option of replication. It's an option, but it's a compulsory kind of a thing. Whenever we lock any location for data processing, we put a lock, we commit some data on some location. The data that's being stored, that will be replicated to some different geographic, replicated at a different geographical location In case of calamities or natural disasters, if we have a storage server in India, in some at a different location in Europe, at some different location in some other parts of China or any kind of place. Whenever we store data, the data is being replicated, stored at 2 to 3 locations, just to uh, recover that data in case of a natural disaster. So this is the HDFS block where data is being uh, stored and the block operations are being done, and how clients search metadata, read data, and how they write data. So this is the Hadoop distributed file system, and we were dealing it with Hadoop. I was working with Hadoop since 2015 or 16, I guess 15. But in the meantime, we came up with a new thing, that Apache Spark. I will not explain this Apache Spark in detail, but we will compare it. We will compare it on the basis of some parameters. The parameters we have, the first parameter is cost. Hadoop is an expensive, is less expensive as it's an open source. It requires more memory on disk, which is relatively inexpensive. Means the operations that are being performed, it performs operations on disk. That disk is less expensive. But Apache Spark requires a lot of RAM. It runs operations within memory. This increases the cluster size and its cost. What does that mean? In Hadoop, we have 64 MB of block, and the cluster size is fixed. But in case of Apache Spark, we need a lot of RAM to execute things. That will increase cost, but the blocks, cluster blocks will increase. Means we can process more bunch of data, more blocks of data in a less span of time, but the cost will be more. In Hadoop, it requires a lot of this. In case of it is less expensive, but it's not fast as compared to Spark. Hadoop is generally slow as it performs operations on disk and cannot deliver near real-time analytics from the data. This is the issue. Spark runs 100 times faster in memory and 10 times faster on disk. Most of the processing is done on the in memory, and a small part is on the disk in case of Spark. But if we run Spark on Yarn with some other demanding resources, there could be a major degradation. Means Yarn is a product of that Hadoop. We will see simply, if we have this Hadoop with us, it will be slow in tackling real-time analytics. But in that thing, Apache Spark is faster. So we call this world today as a global village, a village that is connected. Most of the things are, people need things in real time, very fast. We can compromise on cost, but if the speed is much more, if uh, if it will cost X amount of money processing a thing on Hadoop, and if it will cost X plus 100 on Spark, but if the processing is being done very fast, we can afford that, because the world is so fast that people, organizations, industries, and governments want to process things very fast. Then machine learning. There is a special package, Mahout, in Hadoop for processing data and building models, and a language, Samsara, for processing in-memory algebraic operations and to allow users to write their own algorithms. For writing algorithms, building models, Hadoop has some packages or models or some uh, extra, some other Mahout and Samsara for processing it. But Spark has inbuilt memory machine learning libraries that can be used for classification and regression. And that can also build machine learning pipelines with hyper parameter tuning. So this is in case of it has libraries built, and it has some other tools. Hadoop has some other tools. We have to download them and install them and link those tools with Hadoop, and then use machine learning kind of application and building models. But Hadoop has those inbuilt. Sorry, Apache Spark has MLlib like tools inbuilt within it. The data processing, Hadoop processes data in batches. It's simple, a batch processing kind of a thing. MapReduce operates in sequential steps by reading data from the cluster, performing its operations on data, writing the results back to the cluster. Apache Spark batches real time and graph processing of data. It performs three things at a time. It reads data from the cluster, performs its operations on data, and then writes back to the cluster. The only mode of processing in Hadoop is this sequential steps. That's the batch processing. In Apache Spark, we have batch processing, real time, and the graphical mode also. The scalability. Hadoop is highly scalable, and we can add n number of nodes in a cluster. Yahoo has reportedly used a 42,000 node Hadoop cluster, a cluster that has 42,000 nodes in it. We have the biggest known cluster size and of 8,000 nodes in Apache Spark. But as the data grows as big data grows, its expected cluster size will increase to maintain the throughput expectations. What does that mean? We have more number of nodes in Hadoop cluster, but in Apache Spark, the cluster size is more. If we have less number of nodes, but the size of the cluster will be more, less nodes doing more work, more nodes doing same work. Okay, scalability. Now we have the scheduler. Hadoop MapReduce is dependent on external scheduler like Yarn. But this Apache Spark has an inbuilt scheduler. So comparing this all kind of things from 2014 on the basis of my, it may be correct, or it may be I may be wrong at places where I can say it's my personal experience. I have used Hadoop and I have used Apache Spark. And I'm not using directly the Apache Spark. We have a tool called PySpark. On the front end, we have Python, and at the back end, we have Spark. I am using that tool. I used I used Hadoop for many years. I was teaching this big data course. I used mostly Hadoop. But in case of when I uh, used Apache Spark, I got I gave you some parameters: cost, performance, machine learning, data processing, scalability, scheduler. All these things, all these performance parameters have discussed with you. You may reach to some other conclusion, but I have reached to a conclusion that I then switch it to this Apache Spark. That Apache Spark has a special package, special kind of a thing. We call it PySpark. I installed it, and in the front end, I did programming in Python because Python has a lot of libraries. When we compare, first of all, For Hadoop, I had some issues like only I was able to use. I had to write a lot of codes to eliminate that kind of a thing. Python has a lot of libraries in it. There are some things in which you must have you must have to write 100 lines of code. That 100 lines of code is done in Python in just 3 to 4 lines. It's already inbuilt in its library. The code is also already written. We have to use simply its library. We have to just like we have using linear regression, logistic regression, other kind of things, mathematical kind of things, some algebraic kind of things. They're already done, and we have a lot of help for Python. That's why I switched to Python from Hadoop. And what we are doing, we are moving to Apache, and I moved to Apache Spark. That is the its version, that is PySpark, and on the front end I was using Python, and at the back end Apache Spark was there. So, what kind of analysis what was I doing? This is the data. First, IoT. I will recap in a minute. First, IoT devices, they generate data. The data is being stored somewhere. When the data moved beyond the capacity of a machine to process it, to analyze it, to perform operations on it, we move to the next level. We stored it at some location on a machine which has the capacity to handle that data. This data we call it big data, a machine which is more powerful, which has a server or some other kind of a thing, where we can put that data and we can go for the analysis. We are storing data for the purpose of analyzing it. The second thing, first is data generation, that's through IoT devices, then the data storage, then the data processing, then the data analysis. When we move to this analysis is of three types: the descriptive analysis, the predictive analysis, and the perspective analysis. Three analytics types. The descriptive analysis, we have a lot of data, historical data. We want to find out. I have a data of students of BTech first semester to eighth semester. The data we have is the data stored from last 30 years. I want to see the trends. Tell me any subject in computer science engineering or information technology engineering. uh, in our department in information technology, I want to check. The department was established in 2007. In these 13 years, what is the trend? Tell me which student subject do students feel the most difficult, where they will have supplementaries, while they fail to pass. I search the data and I go and manually check it, use some algorithm, use some technique to find out what has happened in past. When I will check it out, what happened from the existing kind of things, there are things what has happened in the past 70 years. Elections are being performed. What is the trend? How things are going? We call it descriptive analytics. What happened in past? We analyze it. The second is predictive analysis. The predictive analysis will show me what will be the future. For example, based on the historical data, I will see what is the historical data. On the basis of that historical data, what I will do, I will predict the future. How I will predict? There is a subject called TOC, Theory of Computation. I will check the trends that in past 13 years, 10% students only passed. Those who were attending their classes regularly and who were practicing that subject mostly, who discussed them that subject, And I will move to that descriptive analytics, see to see the behavior of students in relation to that subject. And if I will check the behavior of students in this on a particular subject, I want to predict how this class will behave. And I will check historical data. I will see some trends. I can predict there are chances that 10% of students can only pass, 30% of students can only pass on the basis of historical data. What will happen in future? I'm tossing a coin. What is the probability of coming a head? What is the probability of coming a tail? So there are two options only, head or tail. So the prediction, I can go for prediction. The uh, most likely thing to happen, it can be head or it can be tail. So there is weather. I will see the behavior of clouds. Is uh, are the clouds dense? Do they have water contents in them? What is the speed with which they are traveling towards our location or geographical location? I will, on the basis of those clouds, the intensity, the amount of clouds, and the all the things related to and the season in which the clouds are, I can predict whether it be if there are dense clouds in my location in Srinagar here in today's time. I can predict there can be snow because the season we are in winter. There are chances that there will be snow. But if we have similar kind of clouds, but it's the month of June, then we can predict that there are chances it will rain. So this is the what will happen in future on the basis of some basic things, basic prerequisite knowledge about a particular incidents. I will predict what will be the future. And the third is perspective analysis. How can we make things happen? It's simply the combination of two. We will use descriptive as well as predictive analysis to make things happen. These are the three techniques of analysis. What we are analyzing, an IoT data that's being generated by IoT devices that we have stored at some location. When we store that in some location, when the storage and the volume of the data goes beyond the capacity that my machine can process, when the velocity of data goes on increasing and increasing, and when the variety of the data goes on changing, so we call it, this is the big data. Now we have to analyze it. Analyzing the big data, we used some tools like Hadoop and Apache Spark. For that purpose, what we have used a tool, we call it PySpark. And on that tool, what we are analyzing, and we have three types of analysis, that is descriptive analysis, predictive analysis, and perspective analysis. And we will move to the next stage. I guess this is the last slide. Design of analytics process. I have used a use case here. We have recently published a book chapter called Descriptive, Predictive, and Perspective Analytics in Healthcare. We have used the use case healthcare there. Simple. What are the rules of healthcare and the data under study? We are using data collection and integration, and simply we are going for the, this is the history. Whenever we store data, that when the data is stored in past, we first we will go for some descriptive analysis, see the outcome, store the data in the database, and then we can collect the data and directly go to the database and see how we can predict the data, and then we pass that feedback to the descriptive analytics, and then we can go for perspective analysis with a feedback moving back with this the back propagation, and similarly we will have some results at the front end. This is the whole process of analytics what we have seen till now. So the topic was data, IoT, big data. So up to this point, we have been able to see an IoT device and a cloud server, where we have the server that has processing, huge storage, and all the resources in abundance. We can hire those resources, we can use those resources, but it's not easy for us every time to go to cloud as a user, as a person at the ground level, as a IoT device, to move to that cloud every time. There will be some cost of going, latency will be there. So we have placed an intermediate device between cloud and that IoT device, a fog device or an edge device. We will perform processing on that fog or edge device, where then we will move to the next level. If fog device will not be able to fulfill my needs, I will move to the cloud. So the latency will be less. We will be able to perform operations in a less amount of time. So we have till now we have completed this presentation, but I was working on a project. So this paper, I will show you a bit. This is being published in IEEE. So distributed deep neural networks over cloud, edge, and end devices. So this paper has proposed a model. Simply, what we can do, we have. I will move to this this diagram. We will, in the first attempt, we have simply a cloud, and in the second phase, we have a cloud and a device, IoT device. We will use this device to generate data and it's connected to the cloud, and this data will be stored there. But we have geographically distributed devices. One device is here and other is here, and they have a local exit, and we will store the data on the cloud. In the second scenario, what we are doing, we are having some IoT devices, and then between them we have edge or fog device and the cloud. So this is the fog IoT device, and we have edge devices. There are many IoT devices that are being connected, and in this case, we have this is the cloud and edge devices, but geographically we have different edges and different nodes. They are connected. We have this F scenario. We mostly deal with these scenarios. We have cloud at the top, different edge devices connect to the different IoT devices, and different IoT devices, uh, different edge devices connected to different IoT devices, and they generate data and they process data, and then have some connectivity with cloud. Now, what we are trying to do, we have in this paper, it has been they have performed it like this. They are capturing data from different devices, 6 devices at the same time, and then this they are trying to find out the accuracy, and this is the threshold. We know that entropy kind of a thing we have. When we have the less entropy, we will have more accuracy. We have this paper has placed the values of entropy, exit threshold values between 0 and 1, and then accuracy between 0 to 100, the overall accuracy, and the local exit accuracy. Overall accuracy is this one, and the local exit accuracy is moving from zero, from this 75 to 100. The scaling, when we scale data, what is the impact of exit threshold and what is the impact of scaling end devices? When we increase the number of devices, we have three scenarios. The first scenario is in which we have simply an IoT device and a cloud IoT device, and second scenario, the IoT device only performs at the individual level. Processing is performed at the individual level. And the third scenario is we have edge devices in between. The first case is here. This is the overall accuracy, classification accuracy. This is the cloud based, second one. The third one here is the local, and this is the individual. See how when the number of devices go on increasing, how classification accuracy increases. So data, this classification accuracy goes on increasing uh, from point to point when we increase the number of devices. In the similar way, this paper has discussed classification accuracy and the communication overhead. This way, it goes on increasing when the communication cost increases. The classification accuracy means the accuracy of classification at the fog nodes with limited resources will be less because we have communication cost less. The efficiency will be less. But when we will offload the data, offload this, what we can say, um, data to cloud, we will have communication overhead, communication cost, but the accuracy will be more. Similarly, we have fault tolerance. This is the way how we are fault tolerant in case of uh, individual devices and in case of devices connected to fog and connected to this, what I can say, uh, individual devices that are individually performing the things, and the devices which are moving the data, offloading the data to the cloud. So we have, just I will, so I will use this PySpark. I have executed this code. This one. So this code I've been executing this. I will run this. This I'm importing matplotlib, a library, and and numpy, and inserting the data values and the cameras, and this will show me the behavior local when connected to cloud. The accuracy will be more when the accuracy of these cameras, number of cameras, and the accuracy levels will go on increasing when we move the data to the cloud. Individual level, at individual level, here the accuracy is zero point 0.2 around, and here we have 0.55 in case of similar thing when done in cloud. When we have two cameras, the accuracy level is zero point 0.2 for individual. For edge exit, yeah, fog exit, at the fog level we have 4, and at the same thing at the cloud we have 0.777. Similarly, it goes on increasing. Now moving next, we will see this. This is the missing cameras and accuracy, and similarly I have accuracy versus communication overhead. Okay, and this one, is the accuracy versus communication. Accuracy, for this is the overall accuracy, and this is the behavior, how it shows accurate, how much data is accurate. And at threshold, when the entropy is more, the accuracy goes to the dip. Here it will move to this value. Locally exited, when it's locally exited, it will be around 121. And but in case of accuracy, it's going to below 0.92. But in case of when entropy is zero, the we will have accuracy that is 0.96. So similarly, all the other plots. So moving to this, I guess we are done with this paper. This paper we had all the graphs. We have written that code in PySpark that worked at the. I had one more paper, but I guess we are short of time. uh, I had done its coding also, and then see, what we have done in seen. We are here. We have a computation offloading algorithm, an algorithm which will offload data to some edge or some cloud, so that we will see how this paper has worked. It has computation overhead of versus time slots, and then bandwidth versus computation overhead, and then these things have been done. And there is an algorithm they have created an algorithm that will offload computations. The important thing in IoT, big data, and 5G, this will be a thing which we can get a solution for. That is the things we have in our IoT devices. We have to always offload them. Or is there any chances that we have some mechanism in which we can solve these things within this, what I can say, within the device? Is there any capability to handle that data? So I guess we are done with this presentation. Thank you.
Yeah, thank you, Kalim, for sharing this very in-depth, thoughtful presentation with some live demonstration as well. Once again, I am requesting all the participants, if you have any query related to this particular domain or the ideas which have been shared in this particular session, you can ask all those queries directly to the expert. You can unmute your mic or directly, or you can post your questions or queries in the chat box. Are we actually live with these participants? Anyone who can respond? Anyone from the participant who is at least active right now? I think there are no queries from the participants, and thank you, Kalim, once again for this.
Thank you, sir.
Okay, you can leave now. Can anyone respond among the participants?
Hello, yes, sir. Assalamualaikum.
Walaikum salam. What's your good name, sir?
It is Shahnaz Qabil.
Okay, great. At least we must have at least some sort of interaction. Even at the time of expert, when I asked for at least some query, you should have responded. We don't have any sort of query, so it would at least look good for the expert as well that some people are listening. है ना? With
Yes, yes,
some,
there should be. There should be
yeah,
at least,
there
yes.
should be at least some sort of interaction. You in both.
Actually, I was on move, so I had my earphones and it was in local transport, so I didn't ask
Okay,
any question. That is why. But there should be interaction, obviously.
we will be joining by one more expert, and I'm just waiting for him. I have just sent him all the credentials, so hope he will join us maybe in few minutes time.
Okay, sir.
Just a minute, sir.